They do talk about, there's a blurb in the section talking about derivatives of complex valued functions, especially when e to the rx, when r is a complex value. Differentiation works the same. So y prime, in other words, this is the real part of the function. They call it RE, the real part of this function. This is the imaginary part of the function. So it's like f of x plus I times g of x. Derivatives of a complex valued function works the same way in that you differentiate the real part, differentiate the imaginary part, keep the I there. Okay? So what's the derivative of this?
Negative sign.
Negative d1 plus d2 sine of x. Okay. Plus, and what's the derivative of this part?
I cos d1 minus d2 cosine x.
Yeah, d1 minus d2 cosine x. Okay. So if you buy that part, and they do have a blurb about complex valued functions and their derivatives. Okay, so let's use the initial conditions. Y of 0 equals 1. If I put y of 0, what's cosine of 0? 1. So I just get d1 plus d2 plus I times, what's sine of 0? 0. Oh, awesome. So that imaginary part knocks off, and I know that y of 0 equals 1. Okay, so this gives us an equation involving these coefficients. d1 plus d2 equals 1. Second initial condition, y prime of 0 equals 1. Y prime of 0, well, sine of 0 is
Negative
0. Cosine 0 is 1. So I need I, d1 minus d2, has to equal 1. Okay. Well, here's a question. How does I times anything equal 1?
Negative I.
Oh, okay. This is a real number. This is a purely imaginary number. I times any constant won't equal 1, or any real number won't equal 1. But this has to equal negative I, doesn't it? Because I times negative I, that's negative I squared. I squared is negative 1. Negate that, you get 1. Okay? So this gives us the equation that d1 minus d2 has to equal negative I. Okay. This equation, I can write this as just what? d1 or d2. How about d2 equals d2 equals 1 minus d1, right? Substitute that into the other equation. I get d1 minus, and d2 is 1 minus d1, and that has to equal negative I. So we get all the minuses. I get 2d1 minus 1 equals negative I. Okay. Add 1 to both sides. 1 minus I. So what does d1 equal? Divide by 2. 1/2 minus I over 2. And just like I said, d1 and d2 could be complex. All right. So hold on to that. And what would then be d2?
1 minus I.
So d2 is 1 minus d1, and that's 1/2 minus I over 2. 1 minus 1/2 is 1/2, and this becomes plus I over 2, right? Okay. Plug these values back into d1 and d2. What's d1 plus d2?
1.
Yeah.
Hmm?
1.
Oh, right, 1/2. You add the real parts, right? Add the real parts and add the imaginary parts. Those cancel out because they come as conjugates. You get minus I over 2 plus I over 2. That gives you 0. You get 1. So d1 plus d2 equals 1 cosine x. And plus I times, and what's d1 minus d2?
Negative I, probably.
All right. Well, we knew that. d1 minus d2 is negative I.
You actually don't have to solve.
Oh, right. We knew that. Yeah.
Yeah.
So we get, and luckily enough, negative I times I, that's
Negative 1.
negative 1. No, it's 1.
Or just 1, sorry.
So we get cosine x plus 1 sine x. And these are my coefficient, 1, real number 1. I made up that example because the values of these functions are nice at 0, but 1 and 1 in this case. You get a real coefficient. These guys could be complex.
Just a question form, is it smarter to do it the way you did it versus when you go back to your y is just d1 pi dx and taking the derivative, just treating I as a constant and making it I d1 e
Yes,
dx?
they go through why you can do that. Any function of the form e to the rx, even if r is complex, would be r.
So this would
e
work
to
out
the
if we
RX.
hadn't substituted it in your own.
Yeah, I think so. Okay. All right. So the point is, we get a combination of those two functions, which I knew, formed the whole space of functions, solution space. Okay. All right. So we are going to look more at complex roots. This case, they're just purely imaginary. There's no real part on these ones. Okay. All right, we're going to look at it. We'll do another example soon enough. But for now, we're going to talk about a higher order. Doesn't necessarily mean harder, but so just like it says on that sheet, is we can, the ideas that we've seen is, can be extended. So we can extend those ideas to higher order linear differential equations. So as an example, and once we get beyond 2, they start putting the derivatives just in regular numeric form, plus 10 y double prime equals 0. So again, it's homogeneous, okay? And homogeneous linear equation and with constant coefficients, our method of attack is, assume the form y equals e to the rx. Okay? And there's only 3 possibilities. I get real solutions or complex solutions, but complex solutions will always come as conjugate pairs. A plus bi, A minus bi. They'll always either come in pairs, so I can't have one complex solution only. We have a third order here. When I put its derivatives, what am I going to get for y triple prime? R cubed e to the rx. Now, I can pull out that e to the rx because that contributes nothing to the equation because e to the rx is never 0. Plus 10, and y double prime would be r squared e to the rx, but factor out the e to the rx, and it doesn't contribute to the solution. That would be my characteristic equation. Okay. So this one, how does this factor? I'm going to factor an r squared out of it. R squared times r plus 10. Good. Well, good news is there are no complex solutions to this. They're all real values, right? What are they?
0, 0, and negative 10.
Mm-hmm. So r equals 0. Now, but I have 2 factors of r. So it appears as a solution. You can think of it 2 times.
R1 equals R2 equals 0.
Right. This is a multiplicity 2, if you remember that word, but this is a repeated root of this equation. Okay? And we get r equals negative 10. Okay. So there's a special little thing. When we get a repeated root, the solutions would be, y equals e to the 0x, right? y2 equals e to the 0x. But if I get a repeated root, I don't just repeat the same function. It turns out, and we'll verify that this is a solution, you pick up a factor of x out front.
What is it?
Oh, and then the other one, e to the rx, e to the negative 10x. So, y?
Oh, let's say y1 though is e to the 0x is just going to be a constant. Oh, right.
Right.
What does that mean?
Mm-hmm. Well, it's a constant function. If you check a constant function, any constant function like 1.
Because there's no y.
Mm-hmm. So the general solution would be c sub 1 e to the 0x, right? Yeah, and I'll write this as a plus c2 x e to the 0x plus c3 e to the negative 10x. So it picks up a linear factor if it's repeated twice. If it had a multiplicity 3 root, we'd have e to the 0x, x e to the 0x, and another one, x squared e to the 0x. So I pick up another factor of x out front for every added multiplicity. All right, of course, e to the 0x is just 1, so I get c1 plus c2x, that's just 1, that's just 1, plus c3 e to the negative 10x. Okay, so you should try verifying this. During break, just kidding. Or over the weekend or something, but show that that does satisfy, for any choice of those constants, does satisfy my original. It's not too hard, pretty direct. Okay. So, yeah, there's a theorem that talks about that, and I'll just write it down. I don't know what theorem it is, but in my own words, if R,
Can you move it up just a little bit?
yes, all right. I think it's so zoomed in I can't get the whole page at once, but if you get a solution, a repeated solution, call it R1. If you get a repeated solution, that's called a multiplicity 2 or higher. So if you get a characteristic, there. So if it's a repeated root of a characteristic equation, say it has multiplicity. Every time I say that word, I think of a Police album, Synchronicity, but different word. No, they did not name their album Multiplicity, but all right.
I'm sure there's people who do music about it.
Yeah. So say it has multiplicity k, where k is a positive integer. Okay. Then the part of the solution corresponding to R1 so that particular root, there may be another, like in this case there was a negative 10, but the part of the solution corresponding to that root R1 is, it would just be c sub 0 e to the R1x plus c sub 1 x to the first e to the R1x plus, and whatever the multiplicity is, this is the first x to the first, and we go all the way up to 1 less than the multiplicity, so this would be c sub k minus 1 x to the k e to the R1x. So if it's a multiplicity 5, you'd have just a regular constant term plus x to the first plus all the way up to x to the 4th e to the Rx. So, oops, that should be k minus 1. So it's 1 less than the multiplicity. So we had a multiplicity 2 root. I have e to the 0x plus x to the first e to the 0x. I don't get an x squared e to the 0x. Yeah?
So in the book they have theorem 6, which is like has the repeated R or whatever,
Mhm.
same thing, but
Yeah.
they have a kind of a different, equation for it. Is that
Mhm.
just mostly for like a second order, or like what?
No,
Like
no,
what?
and no, in fact, from a second order, you wouldn't get higher than a multiplicity two. Because you get, your characteristic equation would be a degree 2 polynomial in R. So you, at most, you could have 2 roots. But if you have a higher order, then you could have higher multiplicity. You know, if I had R cubed equals 0, then that would be a solution of 0, but multiplicity 3.
So what's the difference between this?
Nothing, except my own words.
Okay,
Yeah.
I was just trying to
Yeah.
figure out.
I just try to,
No, okay.
I chew on it for a while and think about how I'd want to say it. Okay. All right. It's pretty much the same thing. Yeah. All right. So there may be other roots, like the -10 here, and I might have that, but just that part of the solution that corresponds to the repeated root in all those terms. All right. Stuff. And I do want to talk about complex roots again. We did one example for warm-up. Complex roots. So let's look to find the general solution to the equation y double prime. So this is just a second order again, plus y prime plus y equals 0. So it's a lot like the last one, except that I also have a y prime term, and this would obviously change the characteristic equation. So making that assumption that the solution is in form e to the rx, what would we get for the characteristic equation? Y double prime would be, and factoring out the e to the rx, right?
R squared plus R
Plus 1, yeah, that would just be e to the rx, and so factor out the e to the rx, I'd have a 1 left over equals 0. And that doesn't factor, but we got the mighty quadratic formula. It's amazing that at this level, you know, things like the quadratic formula in the fundamental theorem of algebra come into play. The fundamental theorem of algebra.
What's that?
We'll talk about that. Yeah.
Okay.
Yeah, there's a fundamental theorem of calculus. That's the last one you remember being called fundamental theorem of.
It's like
There's also a fundamental theorem of algebra.
it's like Gauss's thing about roots.
Fundamental theorem of arithmetic. Wow. And they're not fundamental in arithmetic. It's got to be easy. It's about adding fractions. No, it's about prime numbers in arithmetic.
What makes it so fundamental?
Well, we'll talk about it. Come to office hours. We'll talk about fundamental, the FTA. All right. -1. Oh, yeah. Let's use the quadratic formula on this. Opposite of b, that's that coefficient there, plus or minus square root b squared, that's just 1, minus 4ac, and those are both 1, all over 2a, a is 1. So what do we get? -1 plus or minus root -3 over 2. So this is going to be complex, right? Complex roots. And this would be, I could write this as -1/2 plus or minus, and square root of -3 is just what we call root 3i, right? I'm going to write this I times root 3 over 2. So complex. And they come in pairs. -1/2 plus root 3 over 2i, -1/2 minus root 3 over 2i. So these are complex. Complex conjugates, always conjugates. The fundamental theorem of algebra says that an nth degree equation, if you count complex solutions, has exactly n solutions. It may not have that many real solutions. This has 0 real number solutions, but it has 2 complex solutions. If you have a 5th degree polynomial equation, you will have exactly 5 solutions. Some of those may be complex. Okay? Yeah.
So in this case, isn't it, or would we leave it in that form, or would we apply Euler's whatever thing?
Yeah, we're gonna do a little bit of that. So, oh, by the way, again, this is called the real part of the number, and the root 3 over 2 imaginary part. Okay. All right, so, well, we get to form e to the rx, and that's our r. And we got 2 solutions. They are distinct complex solutions. So our y, general solution would be some coefficient, some value coefficient, e to the -1/2 plus I times root 3 over 2x. That's r, that's x. Plus d2 e to the r, and take the minus, -1/2 minus I root 3 over 2x. Right? That doesn't look fun.
Pretty.
Okay.
You could make it a little more fun.
Yeah, we're going to do some stuff. Now, one thing I can do is use the exponent properties of a sum, right? So this will be d1 e to, and distribute the x. I'll have -1/2 x, or -x over 2, times e to the I root 3 over 2x. So I'm using the sum and the exponent. So this will be I times root 3 over 2x plus d2. Same thing here, distribute the x. I'll have e to the -x over 2 times e to the -I root 3 over 2x. All right. Oh, we could factor out, look at this. This is going to be part of the real part. I have e to the -x over 2. Factor that out. We got d1 e to the I root 3 over 2x. We factor out the e to that, and so we got plus d2 e to the -I root 3 over 2x. Okay. So again, where d1 and d2 could be complex coefficients. But what I want to show you is not the derivation so much as if we use Euler's formula here, like we did in this case. If we use Euler's formula to write this as cosine root 3 over 2x plus I sine root 3 over 2x. I could do that to both, combine like terms, we'll save some of the steps, but what we're going to get is e to the -x over 2, and there will be some combining because I'm going to have a d1 cosine root 3 over 2x, d2 cosine root 3 over 2x. Combine this all up and we'll have new coefficients. I'm just going to call them C1 and C2 now. But we have C1 cosine root 3 over 2x plus C2 sine root 3 over 2x. All right, somewhere in this jumble, in this magic, the imaginary part would disappear. These would be real coefficients, like we saw in that one example. So that's all I'm going to do as far as particular examples. But we'll just know that we get something of this form. So complex coefficients, if I get complex solutions, not just imaginary, but pure complex, a plus bi. If I have a real part to it, that pops out here. The -1/2 was the real part of that solution. Right? There's the real part, and here it is, negative 1/2 x. Okay? Plus cosine root 3 over 2x plus sine root 3 over 2x. So these guys are your imaginary part. And the negative 1/2 is the real part. Okay. Oh, and I should mention formally where C1 and C2 will be real coefficients. Yeah.
So you could take this, I guess, the other direction. You could say anything that you see of the form sine or cosine is a imaginary solution.
Say it again.
So you could so anytime you use like sine and cosine to get this to as the solution, you can take that in reverse. You can rule that's all it is, an imaginary solution to the y of x, or
Well, no, this is a real function. This is a real value function.
okay.
They do talk about, and you know, it's not a complex analysis class. They talked about complex solutions to differential equations, and you can't have that. We're not going to deal with complex solutions, complex functions.
Okay.
This turns into a real value function,
Right.
even when I get complex solutions to the characteristic equation. So, what we're coming up with, just like the fundamental theorem of algebra that says, hey, any polynomial equation, degree n, you will get exactly n solutions if you admit complex. Each one of those, even if it's complex, yields a real solution to the original differential equation. So every one will have a form. Basically what that's saying is every linear differential equation, homogeneous, will have solution to the form e to the rx, whether or not r is complex or real. Okay? They just take on different forms in different cases. Okay? So one thing I want to note with this, and it does get tricky knowing where everything goes. Moral of this story. If the characteristic equation has complex roots, and purely complex, of the form, you know, a plus bi and a minus bi. Non-repeated, we're not going to consider the case where they're repeated complex roots. That's beyond what I wanted to talk about. Okay? If they are distinct but purely complex, then the form of the solution, you'll notice that the real part of the solution, the negative 1/2, became the power up here, negative 1/2 x. And the imaginary part becomes the argument, inside the argument of the cosine sign. So you get e to the real part, ax, and then any coefficients, c1, cosine bx, that's the imaginary part, plus c2 sine bx. So even when they're, end result of the story, even when they're complex, you do get something of the form, linear combination of sine and cosine, but, you know, there'll be some b in here. And if you get a complex conjugate, if they're pure complex numbers, you have this e to the x factor out front, where that comes from the real part of the solution of the characteristic.